Today we study orthogonality, which is a fancy word for vectors being perfectly perpendicular. These vectors refuse to cooperate or oppose each other in any directional way. Orthogonal means perpendicular, and for vectors that happens exactly when the dot product is 0. So if the dot product is 0, the vectors are basically ignoring each other. To test orthogonality, compute the dot product. If the answer is 0, congratulations, the vectors are perpendicular and emotionally unavailable. A normal vector is perpendicular to the whole line or plane. So the point-normal equation is basically geometry saying, start from a known point, then force perpendicularity. This is the point-normal form of a line. It looks fancy, but really it just says the displacement along the line must stay perpendicular to the normal vector. Same idea as the line, just one more coordinate because 3D is more fancy. The coefficients of x, y, and z are the components of the normal vector. So the normal vector is hiding in plain sight inside the equation. Plug the point and normal vector into the formula and simplify. This is one of those rare times where the formula does almost all the work for you. A plane parallel to the yz plane has x fixed. Since the point has x-coordinate -1, the whole plane lives there forever. Projection means splitting a vector into a part along vector a direction and a leftover part perpendicular to it. It is like separating a person's effort into useful work and chaos. This theorem says the split is unique. So there is exactly one shadow of you on A, and exactly one leftover piece that sticks straight out. First compute the dot product and the norm squared, then use the projection formula. The leftover part is just you minus its shadow. Very cinematic. This gives the length of the shadow without finding the whole projection vector. It is the lazy but efficient version, which honestly deserves respect. Since the line makes angle theta with the x-axis, its unit direction vector is cosine theta, sine theta. Trig enters the chat, as usual. The dot product gives how much of u points along the line, and then we multiply by the unit direction vector to build the projection. The usual Pythagorean theorem is just a special case of this. So yes, even in n-space, right triangles behave Pythagorean. These formulas come from projection. Consider any point on the line or the plane. Now think of the vector that goes from this arbitrary point to the given point. Distance is just the length of this perpendicular drop, which is geometry's version of taking the shortest legal route. The proof is really just projection wearing a fake mustache. Once you see that, the formula stops looking magical and starts looking suspiciously reasonable. Plug into the formula carefully and do not let the negatives start a riot. The denominator is just the norm of the normal vector. To find the distance between parallel planes, pick a point on one plane and measure its distance to the other plane. It is a neat trick and way less painful than inventing a new formula. Once both planes have the same normal vector, they are parallel and it makes sense to be curious about the distance. The hardest part is usually resisting the urge to overcomplicate. Orthogonality is everywhere in linear algebra. It helps us describe lines and planes, split vectors into useful pieces, and measure distance cleanly. Perpendicularity is more powerful than it looks.